In section 1.3, we talk about the basics of something called propositional logic. To illustrate the type of reasoning that we're going to do here, I want to start off with a sort of a common kind of logic puzzle. Imagine living on an island where every person on the island is either of a tribe that always tells the truth or a tribe that is always lying. Raymond Smullyan wrote a book about these kinds of puzzles, and the idea of the book, or the idea of the puzzles, are that when you come across a group of people that live on this island, somehow overhearing their conversation allows you to tell which tribe each person belongs to. So suppose, as a simple example, suppose we have two inhabitants, A and B, and A says we are both telling the truth, and B says A is lying. And so the question is, can you tell which tribe each person comes from? And they could come from the same tribe. They could both be telling the truth, they could both be lying, or one could be telling the truth and one could be lying. So when you try to solve a puzzle like this, what your brain is basically doing is running through possible scenarios for what types of people A and B could be until you find one that's consistent with what A and B says. So if we want to formalize that, we could make a table where in each row of the table we have a different scenario for what type of people A and B are. And so you can see with two people there are 4 scenarios. And then in each scenario we can consider the statements that each person says. Now the key to solving the puzzle is to not have your brain go round and round in circles, and the way we could do that is by considering the statements that they say and not worry so much about who says what. But by thinking of it that way, we'll sort of discover an important tool that we can use in propositional logic in general. So in each scenario, we can consider each of the statements that the person says. So what I'm going to do is I'm going to take a scenario, and then I'm going to take a statement that was stated, and I don't care who said it. It could be written on the side of a barn for all I care. But I want to look in every scenario and decide whether this is a true statement or a false statement. The statement that both A and B are truth tellers is obviously only true in scenario 1, and so I'm going to mark that with T for true. That statement would be false in the other 3 scenarios, because in each of these scenarios, A and B are not both truth tellers. All right? And so similarly, the statement A is a liar, that is a false statement in scenario 1, because scenario 1 clearly says A is a truth teller. So the statement A is a liar would be false. Same for scenario 2. And then in scenario 3 and 4, the statement A is a liar is a true statement. So this does help us solve the puzzle, because what we're looking for to solve the puzzle is a consistency between the truth value of what was said and the truthfulness of the person. So you'll notice that only in this one scenario, only in scenario 3, is it the case that in the scenario A is a liar, and the statement that A said, which is this statement, was false, and B is a truth teller, and the statement that B said is true. So what we're looking for to solve the puzzle is just a consistency between the type of person A and B are and the truthfulness of what A and B says. But a really important idea is that we were able to do this analysis about the truthfulness of the statements in every scenario without having to worry about who was saying what. And so this idea of being able to analyze the truthfulness of a statement in every imaginable scenario is the idea of a truth table. And that's something that we're going to use as our primary tool in studying propositional logic. So in propositional logic, we're going to do 2 things. We imagine we have what are called propositions that are simple statements that are either true or false and unambiguous. And then we're going to use those statements along with some other symbols to express more complicated ideas. And so once we're able to do that, the fundamental question that we're interested in propositional logic is in what scenarios regarding the truthfulness of the component statements are the complicated statement true or false. So this table that we just made is really going to be the main thing we're going to be trying to do in propositional logic, but obviously we're not going to spend our time using this just with logic puzzles. So examples of propositions would be for the puzzle, would be just these two statements that we're building off of. So I might use the letter P for the statement A is a truth teller, and I might use the letter Q for B as a truth teller. The rules of the island tell us that those statements are definitely either true or false, and there's no ambiguity. And that's the only requirement we have for simple propositions. The connectives we're going to use to be able to put these small statements together into more complicated statements are and, not, and or. So we'll use this symbol for the word and, we'll use this symbol for the word or, and we'll use this symbol for the word not. So in our puzzle, the statement A and B are, in our puzzle, the statement A and B are truth tellers can be expressed using the symbols P and Q. And you'll notice I read that symbol just as the word and. So P and Q. The statement A is lying would be written this way because A is lying is equivalent to saying it is not the case that P is true. In other words, it is not the case that A is a truth teller. And again, by the rules of the island, that means that A is a liar. So the actual statements that we analyzed a minute ago then would be written this way. This statement is the statement that A and B are both truth tellers. This statement is the statement that A is a liar. You can see that I've copied the same true and false values that I had before. These are still my possible scenarios, but notice that now there's really no context for this. Regardless of what P and Q stand for, these are all the possible scenarios for the truthfulness of P and Q. And within any of those scenarios, this is the truthfulness of the compound statement based on what the English words mean. So P and Q should only be true in the scenario that P and Q are both true and should be false any other time. Not P should be true exactly when P is false. So only when the scenario where P is false is not P true, and anytime P is true, then not P is false. So the main observation here is that these truth tables are correct regardless of what the statements P and Q are. So they're not particular to the logic puzzle. So what other kinds of statements can we represent using propositional logic? Well, there are lots of statements we can represent using propositional logic. And so part of what we do in this section is to practice going back and forth between the propositional representation of sentences and their English representation. So for example, if the propositional variable C stands for Sue is a computer science major, and the propositional variable J stands for Sue is a junior, and again, these are unambiguously true or false as long as we know who Sue is, then a statement like Sue is a junior computer science major would be represented as C and J. Notice the English sentence doesn't have the word and in it, but it expresses the idea that Sue is both a junior and a computer science major. And so I would write that as C and J. In the second example, Sue is a computer science major, but she is not a junior. You may object that we haven't defined a symbol for the word but. However, if you think about it, the word but is really nothing more than an equivalent to the word and. In other words, this sentence doesn't mean anything different if I put the word and there. We usually use the word but as a conjunction, as an and statement, when the thing that we are adding on is somehow negative. There's a tendency for us to do that in the English language, but logically it means exactly the same thing. So I would represent this as C and not J. And then finally, Sue is a junior or computer science major, but not both. We could write that exactly as it falls out. So junior or computer science major. So the V is our or symbol. But we said was an and statement, not both. So not both junior and computer science major. So that is a compound, very compound propositional logic statement. And that's not the only way to represent that. But that would be a good way to represent that idea. That does raise one idea, one note about the word or. In our propositional logic that we study in our class, the word or here is what we call the inclusive or, meaning that it does not rule out the possibility of both. There is something called the exclusive or that sometimes people use. Sort of, if you emphasize the word or in an English sentence, you're sort of being exclusive. The exclusive or comes up when you're trying to choose between things. So if you say you're either a freshman or a sophomore, there's an assumption there that you can't be both. So, and that's a problem with the ambiguity of the English language, that sometimes the word or in English, especially if it's sort of stressed, has an implicit meaning of also meaning not both. Because we're trying to formalize things so that we have a consistent interpretation, we will always use the inclusive or, which means that either of the two things or both are true. So speaking of the word or, we already wrote down a basic truth table for two statements connected by an and symbol, and we wrote down the truth table when you have a statement with a not out in front of it, but we have not talked about the truth table when there's an or statement. And so the fact that this is an inclusive or means that P or Q should be true in every scenario where either of the two things is true, including the case where they're both. So really the only time an or statement, P or Q, is not true would be when both the Q and the P and the Q are false.